So I'll start in August. Is that right? Yes. Yeah, that's good. Yeah.
All right, our next speaker is Antoine, who told me today that I don't pronounce his name correctly, but yeah, that's how I'm pronouncing it today. And he's going to talk about instability of an anisotropic micropolar.
Thank you. So, since I don't expect people to know what micropolar fluids are, to be terribly familiar with them, I'm going to start by talking about what they are, and then I'll tell you what this anisotropy means and sort of why they're interesting subclass to study. But before I say anything else, all of this is joint work with Ian Tice from Carnegie Mellon. So let's start with just talking about what these micropolar fluids are. And we're going to kick things off with a surprise quiz. The question for you. What is the common feature or a common feature of all of these systems?
Olive and milk sounds like a bad deli option.
They're all pretty bad deli options.
Yeah, that's true.
That's a common feature.
They have stuff swimming in them, Antoine.
They have tiny little things in the fluids in every case. Yeah. So that's sorry. So there's so in there, I don't remember what the particles actually are, but they have an important. The fact that they're there is important because it changes the effective viscosity of the fluid there, which is important when you're making knee replacement prosthetics. You want to make sure they behave like the real thing. So this is the common feature they all have, which is that either there are microscopic particles sort of suspended in the fluid, or the particles that constitute the fluid themselves have particular interesting geometry. These are the contexts that we're interested in, where either things in the fluid or the constituting particles have microscopic structure by themselves. So now, where are these equations going to come from? If I just plot it down on the first slide, that might be a bit much and I might lose you a bit too quickly. So instead, we're going to think about where these equations are coming from. And the way we're going to do this is we're going to first recap briefly how you would arrive to Navier-Stokes on just continuum mechanics axioms. That's one of the ways you can do it. And then we'll see how, when you just start asking that there's micropolar microstructure in your fluid, what the changes are and what equations you get. So this will be our introduction and warming up before we can see the full equations. So if I want to describe continuum mechanics in the very classical setting, I need to know where my continuum is at time 0. I need to know where it is at time t later on. And then there's different ways I can describe things. I could describe things fully by giving a flow map that tells me where the particles are going from Lagrangian to Eulerian coordinates. But in practice, for a fluid in the lab, you can't really measure this, and you can measure velocity. That's why we always freeze everything in terms of velocity. One of the reasons. Now, when we have things suspended in the fluid, when the particles that constitute the fluids are there, there's additional things we need to keep track of. And although I showed you pictures of things like ferrofluid, here the only physical property of these particles we'll track will be due to their inertia. So there's these little particles of interesting geometry, more or less interesting, that's up to us, but they have some interesting geometry and you have to keep track of that. So we have to know where it is at time 0, where it goes at time t. And then again, there's two choices for how to describe this. You can just keep track of how they're rotating at every point for all time, or you can keep track of their angular velocity instead. And again, that's the thing that you sort of have more access to, let's say in a lab environment. And that also makes your, when you phrase your equations in Eulerian coordinates, this is the natural thing to use. So now when I have micropolar fluids, and the polar specifically, polar means that all that these particles can do is just rotate, and basically translate, move along the fluid and rotate. They're not elastic, this model. So these are the things I have to keep track of: velocity, inertia, and angular velocity. Those are going to be my unknowns. And since I'm talking about microinertia, maybe it's just a way to both fix notation and also make sure we're on the same page in case rigid body mechanics has been something we looked at a very long time ago. Let's do a quick recap. If I have a rigid body, and rigid means it only translates and rotates, then what I need to do to describe the body is to tell you how it's translating, how its center of mass is translating, and I need to tell you how it's rotating. And then of course, there's an analogous description in terms of, it's a dynamical description in terms of the velocities. So I need to tell the velocity of the translation and the angular velocity of the rotation. And then one thing so I'm just pointing out this is a classical thing, but it helps understand when we talk about micro inertia and moments of inertia in a second. The angular velocity really naturally comes out to be a skew-symmetric tensor, but in 3 dimensions, you might as well associate those with vectors via just the action of the tensor is the cross product. This is classical stuff that I'm pointing out because it helps us understand a bit more what these moments of inertia look like in a second. So if I want to describe a rigid body, I need to know the speed at which it's translating and the angular velocity at which it's rotating. And then when I want to talk about physics, I need to talk about the conserved quantities. So of course, I'm going to have the mass, which is essentially how it responds to forces. I'm pointing this out because this will play a role when we look at how you derive the equations for micropolar fluids in a second. And then the moment of inertia is how it responds to torques. Right? These are rigid bodies. They're not point particles in our models. They're point particles with geometry in some sense. So they respond to torques in particular ways, depending on their geometry. And then the moment inertia you compute in this way. And it's to explain this expression that I talked about how angular velocity ought to be a tensor, but we identify it with a vector. This really should be the variance of my mass distribution, but because I made that identification, you get something that's kind of like a variance. So the point is you can just compute these things easily if you know what the distribution of the mass of your body is. And for us, where we care about the dynamics of this, what's nice is that as it evolves, it's just conjugate to what it was at time 0. This is nice because its eigenvalues are preserved, and that's how we're going to characterize the geometry in simple terms. Depending on how many repeat eigenvalues and things like that it has, it will tell you how simple of a geometry it has. Those eigenvalues are the same, it means it's basically a sphere. Or if it's a repeated one, then you have an axis of symmetry and things like that. And that will be important later when we talk about instability, because the geometry of my particles will determine whether I'm stable or unstable. And that will characterize in terms of these eigenvalues, which are preserved by this.
Can you remind what R was again?
Oh yeah, I probably didn't write it actually. It's a rotation. I think I had a Q before, but the Q was the one for the actual full continuum. Or it's just a rotation of this about its center. And then once you have the mass and moment of inertia, and you also have the velocity and angular velocity, you can compute all the other physical quantities you want, namely the conserved ones. So you have the momentum, angular momentum, you can have kinetic energies, all the other things that you want to see conserved. The reason I point those out is because when we're going to motivate where the equations come from, it's going to come from balance laws from these things. So the full picture, again, let's go back to this. These little microscopic bodies are translating and rotating, and we're keeping track of velocity, angular velocity, and the microinertia. The microinertia is the moment of inertia of these microscopic particles. And so now, where are these equations going to come from? Well, there's many ways you can, especially formally, as what we've done in one slide, there's many ways you can derive Navier-Stokes. I'm going to do it in sort of an axiomatic continuum mechanical way. And then we'll do the same thing for the micropolar case and see what comes up. So Navier-Stokes, I start out with conservation laws. I add that my mass is conserved, so my mass density is conserved by the flow. I'm going to do the incompressible case because that's the one we'll actually study in a minute. Could do the same thing in the compressible case as well. So incompressible, so this is advection of mass. Linear momentum is conserved. And then I'm going to belay a very simple point because it will come back in a second in the micropolar case and it will be important. So the very simple point to belay is this. This is conservation of linear momentum, but I can use conservation of mass to simplify it. So I can simplify this. The point is something similar will happen to the conservation of angular momentum when we go with micropolars, and a very important term is going to come out. So I wanted to really spend time on this. And then you have angular momentum is conserved, although it doesn't look like much in this case. It really manifests through the symmetry of this T. And I didn't tell you what this is, so I probably this is a good time to do it. This is the stress tensor. This tells you how the fluid responds to forces it exerts on itself. And this is really where you're going to bake some of the physics of your fluid. Different fluids behave differently because they have different stress tensors. They respond to forces in different ways. They're viscous or not, for example. Right, so this is where you really start to do fluid-specific things. You go in the lab, you measure how your fluid responds to various things, and then you say, okay, well, in some regimes, if it's Newtonian, it depends linearly on things like the gradient of velocity and maybe on the velocity itself. But then you also say, okay, my equations of motion better be frame invariant. It shouldn't matter where I do the experiment or which way I look at it. That simplifies things greatly. My stress tensor can actually only depend on the symmetric part of my gradient. So in the incompressible case, you get the symmetric part of the gradient and then the pressure, which is really a Lagrange multiplier for the incompressibility. You put all of this together and you get incompressible lengths. So this is classical. Now we're going to repeat the same process, but for these micropolar fluids that have these spinny microscopic molecules in them. And we start from the same place. We start from conservation laws. Mass and linear momentum look exactly the same. Angular momentum is a bit more interesting. So the evolution of angular momentum has two source terms in it. M is very similar to T. T was the stress tensor, tells you how the fluid responds to forces it exerts on itself. M tells you how the fluid responds to torques it exerts on itself. There are these things with geometry spinning next to each other. They exert torque on each other. And these torques are mediated, it's built into M. And then you also have vec of T. This is how I take the antisymmetric part of T and then take the associated vector. That's what that means. So that's coupled to, and this is how U will be in here and coupled to W.
So, yeah. So U is the velocity of the mixed fluid and micropolar flow.
The way we're describing it here, it's all the particles in the fluid have this geometry. So it's not a mixture. It's more the case of the liquid crystal fluids or things, where the constituent particles have a particular geometry.
So fluid made up of these like
yes,
bits.
Yeah. And then you also have conservation for your moment of inertia. These things are spinning around, so moment of inertia is conserved in some way. And so this is what you get. Really, the moment of inertia is just, when you differentiate this in time, this is what you get, where the omega j here is just a commutator, omega j minus j omega. The big omega is the 3x3 skew symmetric tensor, little omega is the associated vector. So you have these conservation laws. And now we're coming back to why we bothered spending 10 seconds on linear momentum simplifying.
Why there's no flow in front of the angular momentum?
Because it's in J. The J has the mass comes into play in J, right? Like when you like the moment of inertia, I mean it's like a variance type thing of your mass density. So the mass plays a role in there. Like J omega is like rho u in some sense.
But okay, so if you J is already include information of each particle, like the mass of each particle, then rho is playing the role of how many particles you conjugate at one point. Rho is like a number. So because you're running the microscopic equations, you count all the effect because the forcing is acting on a group of particles.
Yeah, in this case, we're going to take rho to be homogeneous. We can take rho to be a constant. So we're not going to worry about when. Yeah, you have things that get a bit weird when you have doing this in a compressible case is much nicer because then when you start having to think about the total angular momentum of a bunch of these particles next to each other, it gets a bit, or the total moment of inertia gets a bit tricky. So here rho is going to be a constant. And so now, we get to this point where I can simplify the equation for angular momentum using the conservation of micropolar inertia. And this is what you get, so just product rule. But then when you plug this omega j into here, you get omega cross j omega. And this term is important for two reasons. One, it's a manifestation of an important physical phenomena that we'll spend a whole slide talking about later, so we'll talk about that then. And then you'll keep seeing this show up as a root cause of difficulties in the analysis of these models. So you simplify or you rewrite angular momentum in this way with something that looks like what you had for u, but then you have this omega cross j omega term. It's the precession term. That's the physical effect it's about. We'll talk about that in more detail. And then you do the same kind of thing you did before. You say, okay, I go in the lab and I measure how the stress tensor, the coupled stress tensor depends on the dynamical variables. You posit that it's linear in these variables and their gradients. You ask that it's frame invariant, and so you get lots of simplifications. The one to point out in particular is that the curl of u and the rotation of the microscopic particles are coupled in this way. So this will show up as a dissipative term in your equation that is basically driving the system towards having the curl aligning with the rotation of the microparticles. So it's sort of driving the large-scale rotations, the large-scale sort of vorticity to be aligned with the small-scale rotation. But that's not something we're sort of positing. This just comes from frame invariance. And then, okay, this is a bit uglier than before. When you just had Navier-Stokes, you just had this guy. You didn't have all of this. But now this is what your stress tensor looks like, the classical thing, plus a coupling between the curl of u and the microscopic rotation. And then here, this is just a way of writing the gradient of omega into all of its pieces, the trace part, trace the symmetric part, and antisymmetric. I'm using 10 to be the thing that goes backwards from the vec map. So this goes from, this takes a vector to a 3x3 antisymmetric. All right. You put all of this together and you get a beautiful set of equations, which is the following. And this is why we spent a few slides building up to this, because that's kind of a mouthful to start the talk with. And this is in the case where I have some external forces and torque acting on the fluid. This is an initial value problem. And all of these things are conservation laws. The first one is just a regular conservation of the linear momentum. There was no W, this would be the usual thing. Incompressibility, which is conservation of mass, or in this case, conservation of angular momentum looks like this. So on the left, this is just the evolution of angular momentum with this precession term. And on the right, you get a bunch of dissipative term. So these two are just dissipation on omega, and then you have this coupling between u and omega. And then you do conservation of microinertia. So what do we know about this system? Or also where does it come from? So these particular micropolar fluids were introduced in the 60s by Aronjan, and he has textbooks and done a lot of work on those, and there's good sort of exposition summaries of all that is known about them in sort of an engineering perspective in these textbooks. And he has a whole hierarchy of things. I'm talking about the simplest part, which are these micropolar. So polar means rigid. The bodies are just rotating and nothing else. Well, rotating and translating. You could have the body subject to linear elasticity. This is what he calls microstretch. You could have this monster of every little microscopic body satisfies full nonlinear elasticity, and then or down the line, that's quite a mess. But what's interesting is that, so this was introduced in the 60s, but this idea of having internal couples, of having neighboring constituent particles of the fluid sort of acting on each other and having exerting torques on each other, this was already in the Kosovo brothers' work of the early 20th century. They have this sort of treatise on continuum mechanics, and they mention these kind of things in there. So these are all ideas. There's an interesting description of the history of all of these things and many more in continuum mechanics in the book by Moody. Now, when it comes to the math of it, what's very interesting, the mass of it, what's very interesting is that only isotropic micropolar fluids have been studied in a mathematical literature, which means that basically your rigid bodies are spheres, or maybe they're a cube, which means the moment of inertia is at NTC, so inertially the same as a sphere. And in this case, you get basically what you would expect for 2D Navier-Stokes. You get global well-posedness in 2D, and this is a lot of work by Lukasiewicz, was sort of the first to do a lot of this stuff. And then in 3D, you get, it's not quite as nice, you get uniquely strong solutions. I think, so and the first thing that Lukasiewicz did, you had weak solutions locally in time, some more recent works that gets global weak solutions, I think. And then there's all sorts of things that, you do in Navier-Stokes that you try to do in the system. So for example, there's implicit limits and partially implicit limits where you send one of these viscosity coefficients to 0, but not the other, see what happens. So there's a lot of work on this stuff. So there's a lot of work on isotropic macropolar fluids. In 2D, by the way, they have to be isotropic because that's why this curl is a scalar in 2D, right? In 2D, you need a scalar to describe the moment of inertia. But in 3D, they don't have to be. So now, this is where the work we did comes in, which is to study these anisotropic macropolar fluids. These things, because these examples I gave you at the start, most of them, if not all of them, had microscopic structure that was not spherical or not sort of inertially spherical at least. So this is the setup that we're going to look at. We're going to look at an isotropic microstructure, but we're not going to go to the fully general case. We still want an axis of symmetry. So this is what has been studied so far. This is what we'll talk about, things with an axis of symmetry. And I'm breaking it up into two cases because those will be the two cases that behave differently in terms of stability. We'll see that the pancakes are, there's more about the setup I have to tell you, but the punchline will be that the pancakes are stable and the rods are unstable. But okay, I need to give you more details before that sentence really makes sense. So there's an axis of symmetry. We're not going to look at the fully general case where there's no preferred direction. So the microscopic structure has a preferred direction.
Are there any results for the binding stretch?
That's a good question. I don't know. I don't know is the answer.
Then you get even more equations in the microphone.
I mean, it gets much messier because now you have linear elasticity in there. So yeah, that's a good question. I'm not sure exactly the mathematical literature. Like for example, Lukasiewicz has this book on a lot of the stuff that he's done, other people have done on the mathematical theory of micropolar fluids. But the microstructure literature, I had to guess, it's very little. I mean, already when you do fluid-solid interactions, that's hard. And then if you have a solid at every point in the domain, it seems like that would be worse. I haven't looked at it closely. So for us today, we're going to say squarely in the micropolar regime, and in particular in this sort of sweet spot where you have some geometry comes into play, but you still have a preferred axis. And then the other thing is there's going to be a constant microtorque acting on a microstructure. And I should say another thing is that what we're really looking for here is to talk about stability of interesting equilibria. In some sense, that's because, well, this problem has parabolic elements to it. You have a Navier-Stokes type thing built into it. So you're not expecting sort of local bulk cosonance to be necessarily the most interesting thing to study. You're expecting the long-term behavior to maybe reveal more of the physics of what's going on. So you're interested in the stability of some interesting equilibria. What is the simplest way to get this interesting equilibria? You plug in structure with a preferred axis of symmetry, and then you just force it or torque it constantly for the torque acting on the microstructure. But basically, you can think of this as sort of a very toy model of these things that happen for ferrofluids, where the torque is not just a constant, but it has something to do with the external magnetic field. That's that this would be close to modeling. So in this context, there's no external force anymore, and there's a constant torque acting on a microstructure, which is just picked in the vertical direction here, because the whole thing is frame invariant, so you get to choose a direction. Doesn't matter. And the tau is the strength of the external microtorque. And the way we build the preferred axis into the equations is by specifying the spectrum of our microinertia. The microinertia at each point is going to be the same up to a rotation. It's basically the same microparticle everywhere, and it has a preferred direction because there's a plane somewhere and then an axis through it for the single eigenvalue. So that's how the axis of symmetry is built into the equations. And as we pointed out before, this is preserved by the flow as long as it's regular enough, which it will be for us. And so then what is it that we can prove? So in the context of constant microtorque, the microstructure has an axis of symmetry. Well, then there's a unique equilibrium where the microstructure everywhere will just align with the external microtorque. So if I choose the microtorque to be in the vertical direction, the particles everywhere in the fluids will just align with that. They will align with each other, and they're all spinning in the same direction at the same rate. And then what you can prove is that the rods are unstable in L2. So there's going to be a ball in L2 around this equilibrium that you always leave. Oh, to be more complete about the equilibrium. So the angular velocity is just a constant, and the fluid velocity is 0. So the things are not moving around, they're all just spinning in this. So that equilibrium, if your particles are rod-like, then it's unstable in L2. But if you're a pancake, then you're stable in HS with algebraic decay to equilibrium. Basically, what you would have liked would have to get exponential decay. You don't get that. You get algebraic decay, where the rate of decay increases as the regularity index increases. So if you start with very regular data, you decay at a faster rate. And this is sharp in the sense that if you give me a rigid body that's simple enough, like in computing moment of inertia, depending on which one of the two eigenvalues is bigger, is it the one that's repeated or the other one, then I tell you if you're like a rod or like a pancake, and then I tell you which of these two situations are. And in the middle, you're a sphere, and then that's easier. You didn't do it, but you basically expect to get the exponential decay because, well, we'll talk about why later, but basically the system's nicer. In this case, this is a good, maybe I should go back here and pause for questions if there are any before we talk about the. So now that we want to study anisotropic micropolar fluids, what is it that they're gonna make difficult for us? And physically speaking, what are the interesting things about that? Recession is going to be central to everything. Recession is this little omega cross j omega term. I shouldn't belittle it. This guy is very annoying, so it's this very significant. Okay, there's a bit too much going on here to explain precession, so we're going to go to a simpler case. If I just have a freely rotating rigid body, so this freely rotating rigid body, angular momentum is conserved, so it's equal to 0. And then because you have the moment of inertia that is also satisfies an appropriate equation, you can expand things out and you get this theta cross j theta term. So this is precession. This means what? Remember, you get this because the moment of inertia behaves in this way, you plug it in, that's what comes up. This means what? This means that the freely rotating rigid body can have constant angular momentum, but non-constant angular velocity. Or this is what happens when you see, where is it? When you see a spinning top, which doesn't have constant angular velocity, right? Because it's sort of wobbling around, but it has constant angular momentum, at least before friction starts playing too much of a role. With sort of small snapshots, certainly has conserved angular momentum, but it's wobbling, the angular velocity is not constant. So the fact that it can precess is exactly encoded in this omega cross j omega term. So this will make our life difficult, and it's just fundamentally what happens when you have actually symmetric rigid bodies that spin. So now we're going to talk about both cases separately. The things you do are very different. So let's talk about the unstable case first. We're going to talk about very, very high level and naively the strategy. I'm going to linearize about the equilibrium, find the fastest growing mode, and then prove that this mode is in some sense non-linearly stable. That when I'm close to this linear mode in the unstable problem, I really have a solution to the full thing that works. It turns out that the difficulty is really the first part, as in the study, the spectral analysis of the linearization is where the difficulty really is. The estimates that you need to do to then show that it's non-linearly stable are actually pretty straightforward. So I'm not going to talk about that too much. I'm going to talk about the spectral analysis. And fundamentally, the difficulty is this. This precession term means that the linearization is not self-adjoint, and it's easy to see because even before you linearize, when I do an energy estimate and test this precession term against omega, it just goes away. So it's not too much of a surprise that when you linearize, you get something that is Q-symmetric that can mess up your spectrum without you having good access to it by variational characterizations, stuff like that. So since we don't have, since it's not self-adjoint, and there's a lot of very nice tricks that we like that are out of reach for us. Also, I forgot to mention, it might have been hidden somewhere, we're working the torus because we want to forget about boundaries for now. There's some really interesting things that happen with boundaries. I mean, there's lots of interesting things for liquid crystals, for example, and different anchoring conditions you can have at boundaries. It's very interesting, but we're focusing on another aspect of the physics. So we're working on a torus, so I have easy access to all of my Fourier tricks. And then because my operator doesn't have particularly nice structure in terms of adjointness or things like that, you kind of just have to get your hands dirty and just brute force your way through at least part of it to compute the characteristic polynomial and then do some essentially complex analysis tricks on it to try and find where the eigenvalues are and make sure they're where you want them. So it's going to be a proof by picture for us. But to point out the thing that is particularly annoying or difficult is that you have U, you have omega, you have J, you have a bunch of unknowns floating around, you have bazillion viscosity parameters. So you have a degree 8 polynomial with a bunch of parameters in it, and I'm asking you to find its roots, or at least show that it has roots that have positive real parts and that don't go to infinity or something like that.
Thank you.
Okay. So it's not particularly a pleasant experience if you try to brute force your way. So you end up just doing some sort of complex analysis tricks, or at least this part isn't, but you do some complex analysis tricks to make sure you can get the eigenvalues under control. You can easily split your operator into the symmetric and asymmetric part, make sure eigenvalues stay in this box. And then because degree 8 polynomials, degree 8 is just very unreasonable. So you send k to infinity and you get something much easier. You get something that's second order as k goes to infinity. So for high wave numbers, you can compute exactly where the eigenvalues are. They're exactly on the imaginary axis. So if you want the thing to be unstable, these things better come from the right at the next order correction, and they do. When you compute the next order correction, I should probably be a 1 over k here. It depends how you write it. This is the next order correction. These things come from the right here. And all of the other eigenvalues are over there. Right? So here you're nice and happy. You find eigenvalues that are unstable, but they're not too unstable, they're not blowing up, so you're still well closed and everything, but they're unstable. And particularly interesting is that they're getting closer and closer to the imaginary axis as your k approaches infinity. So there's no spectral gap here that you can leverage. You have this sequence, it's the torus, so it's just a sequence, but you have this trajectory going to the imaginary axis. So then once you have this, again, the nonlinear estimates, you have to do them. They're not the hard part of the problem. To keep it was the spectral analysis. So once you do this, then, okay, if your microstructure is rod-like, meaning the repeated eigenvalue is larger than the single one, then your equilibrium where the velocity is 0, angular velocity is just aligned with the microtorque, and then this is your microinertia. Again, your microinertia is aligned with the microtorque, right? Because a single eigenvalue shows up in the vertical direction. So this is the equilibrium, and it's unstable in L2. So there's a small delta ball where, however close to X equilibrium you start in this delta ball, you'll then leave a sigma ball around the equilibrium. It happens at the sort of speed you expect, or on the time scale you expect. So this is unstable in L2. So if you're a rod, this equilibrium is unstable. And so as a summary, what does anisotropy do here? It leads to precession. Precession leads to not being self-adjoint. It leads to a lot of suffering with ugly polynomials. Of course, here I'm paraphrasing a great philosopher. So that's anisotropy in the unstable case.
Just to get a picture, this rod-like equilibrium solution, they're rotating, omega is non-zero, right? So they are rotating.
Yeah, omega is just.
And they're rotating this way or tumbling?
So this is rod-like.
It's like that, I get it, where you.
So what you expect the attractor to be is that they tumble over and they rotate this way. This is what you expect that they would actually, like, all we've shown is that if they don't, if they are close to this, they don't stay there and just start wobbling. But what you expect, sort of from simple, just rigid body computations, is that they will fall over and rotate.
And is that what happens? We don't.
We don't. I mean, that would be the next thing to do. So that's the unstable case. Now let's talk about the stable case.
Sorry. So all the things will either clockwise or anti-clockwise, right?
Yes, they will align with the torque. The torque is the same in everywhere, so then they will just align. Let's talk about the stable case now. There's more dots. Stable case is harder. And at the very naive high level, the strategy in sort of, I think it's 2 or 3 steps, is the following. Again, of course, you're starting from the linear analysis just to see what kind of decay you can expect. Right? There was this thing that you don't get exponential decay, but this algebraic decay that improves the regularity. So that comes from the linear problem. And then what kind of estimates do you get? Is one thing which really I should have pointed out earlier. Our equations had sort of a Navier-Stokes-like thing for U, like a Navier-Stokes-like thing for W. But then for J, for the microinertia, it was just a hyperbolic transport. Right, all the microinertia is doing is rotating and being advected. So it's a parabolic hyperbolic problem. So you have to make sure that the hyperbolic thing is not killing the decay you get from the hyperbolic. It's at a very high level and sort of naive level, that's what could go wrong. And then sort of, yeah, what kind of estimates you have access to, how do you leverage the structure, and then can you control the interaction terms that show up and start taking derivatives and have all the nonlinearities that get in the way. So let's talk about the linear analysis first. And the thing to keep in mind, or the thing to think about here, is why are we going to end up with algebraic decay that improves the regularity? Where does that come from? So as a toy problem, we're going to look at this system, which is a lot more palatable than the much longer equation that I was showing you earlier. But this is really sort of the key part of the system that drives the stability and instability. And where does this A come from? Why do I care about these particular components of the microinertia? It comes from the precession. When I linearize the precession, oh, well, it's going to come from there in a minute, but I guess I'm going to tell you about where the whole system comes from. I just forgot about the advection, forgot about J. Okay, that's fine. This is just some dissipative terms, same as what I had there. And then where does this A come from? When I linearize the omega cross J omega term, the only thing that survives at the linear level is J interacting with omega equilibrium in this way. And then omega equilibrium points in the vertical Z direction. So when you compute what comes out, only these 2 components of J survive. So this just comes from the fact that you're exerting a torque on it, a constant torque. And so there's a couple of elements of J that are singled out as being of interest because they survive in the linearization. But again, all of this comes from precession. This is where a lot of the interest and difficulties come from. And then you want to know how these evolve over time. Well, they're just components of here, so you read off what happens. And when you read out what happens, you basically get just some multiple of omega. And here, in the stable case, this here is positive. In the unstable case, this would be, chi would be negative, and that would, the same kind of argument as I'm going to talk about now, would show you that you're expecting instability. So sort of a lot of the mechanism for instability is built into just this sort of subsystem in your equations. So now, what kind of decay rate do we expect? Well, you just start with energy estimates, and this is what you get. So again, if chi were negative in the unstable case, your energy is not positive definite, which could spell trouble. It turns out it does. That was the first result. In the case where you're stable, at least this is a good energy, and then this looks like a good dissipation. The problem is, of course, that this dissipation only controls the omega part of the energy, not the A part of the energy. And at least personally, this is reminiscent of things that you see, for example, in free boundary problems when you have the sort of viscous water wave problem where you have dissipation of, in the case of free boundaries, the dissipation is on the velocity, and then you have the let's say the graph, the function determines the graph of your free boundary that's just advected, and so you get a part of the energy that is in control of dissipation. So this structure is reminiscent of that, for example. That's something people have confidence. And so then the difficulty is, well, this is what you would like. This is what you would like, and this is what you would get if A wasn't there. If it's purely parabolic, you would get nice exponential decay, go home and you're happy. But A is here. So now the question is, how do I gain control of A? So you bootstrap, you leverage the equation, but the reason I want to go through this in a bit of detail is because then when we do this, we'll see why you end up with this decay rate that is algebraic, and that improves with regularity. That's why it's worth going over this in a little bit of a few lines. So this is my energy of omega and A and L2. My dissipation is omega and H1. So now I want to somehow control this L2 term here. So the problem is I'm kind of stuck because I need to control time derivatives of omega to control anything on A using the equations. Okay, that's fine. Just take a derivative in time and then do the same thing, add them to your energies and dissipation. That's what you get. And now you're in business, right? Now you can start thinking about this because now from this equation here, so let's see, dt omega is in H1, omega is in H1, so this is in H minus 1. Okay, so that's the worst one, so I control A in H minus 1. So that's not great because that's not as good as L2, but at least it's something. And then on the time derivative, I get better because omega is in H1, so I get this in H1. So there's a bit of a problem. I mean, this is better than before because the dissipation controls the A energy in some fashion, but it doesn't control it enough. If you had a full L2 here, then you would be back to what I said before with the exponential rate and be very happy. So here, not quite so lucky. Okay, so this is the problem. We want our dissipation to control the energy, but we're off by one derivative. So what we're going to end up with, if my theta was 1, this would be the good case, the exponential case. So we're going to say, okay, fine, I can't do that because of this gap, but maybe I can get away with something like this. And the reason you get away with something like this is because you do interpolation. If I control A in H minus 1, then I can control A in L2 as long as I also control higher order norms. So let's say HS. You can keep track of this, but the point is that as your S grows, your theta is going to get closer and closer to 0. Yeah, it's better. Okay. Yeah, this to be 0. So okay. So then what does that mean? It means that my energy, so A and L2, which is the energy, I control by the dissipation to some power theta. So that's the theta here. And by some energy at some higher level, so I took S derivatives and have this with power 1 minus theta. So what does this mean? It means that now, right, what I'm highlighting here is that you get this energy by just taking more derivative to your PDE and then adding up the energies you get. So then, as long as your high level energy stays bounded, your low level L2 energy will decay algebraically, where the alpha you can compute explicitly. And the point is that as S increases, theta gets closer and closer to 1, and so alpha gets larger and larger. So as you have more and more regularity, you decay faster and faster. So this is why you don't get exponential decay. And this is why you get algebraic decay that improves with the regularity from interpolation. Okay, so this was step 1, is what kind of decay can you expect? So algebraic decay. Step 2 was what kind of estimates do we get? And I'm going to just highlight one of the things that was interesting about one of the interesting estimates in this problem. So you have this whole mess, and then you're going to have to be taking a bunch of derivatives for your interpolation to go through. So you're going to get a horrible host of commutators from all of these guys. And the question is, which terms do you keep basically to have good energy estimates? What I mean by this is, if I just have an advection equation, I know that the good estimates, the good things to keep are the dt plus u dot grad, because u is divergence free. So I know this is sort of the good operator to keep when I take derivatives, and then I just shove everything else as a interaction nonlinearity term. And then the question is, okay, can I control these things? That was step 3, controlling. So now I don't have this advection equation, I have this sort of advection plus a rotation bit. So we're basically, in this case, the good operator to have is an advection rotation operator. So you have the advection here plus the rotation there. So what this means is that when you take derivatives, so your theta is just a bunch of derivatives of your angular velocity, this is the operator that you want to keep. And then just as before, the example I had in the box was if U is divergence free, then this dt plus U dot grad is a good operator. Well, here, if U and J behave nicely with respect to each other in terms of this equation holding, then this operator is going to be a good one for the purpose of energy estimates. So this is the interesting energy structure or interesting structure that's built into your problem. And then the question is, okay, can I control these interactions? That's going to be the last step for us, or actually, maybe not quite. Yeah, I dropped the dissipation out of it, and I'm putting it back right now to show what it looks like. So when you do this, the point is when you keep the right parts of your nonlinear thing to get good estimates out of it, which is in this case keeping this advection rotation operator. This is what you get. You get an energy with U, omega, and part of J in it, and then the dissipation controls U, controls omega, and it couples U and omega in this way. Remember, A are just two components that show up because you linearized, and those are the only components that survived in the precession. So of course, this is the kinetic energy you expect for a rigid body. Then you have this extra term here, which in terms of energetics, we don't have a good physical analogy. Remember, this is where A came from. And this whole stuff is this equation. So when you do this, you get control of HK norms of U, omega, and A, but you won't get control of the leftover terms that are in J, but not A. All right, let's maybe skip this bit. Actually, I do not skip this bit, but I go through it quickly. So remember, the difficulty here is that you have a parabolic hyperbolic problem. The estimates on the previous slide are from the parabolic part. You have the nice energy dissipation things, you're expecting things to decay. But it only controls part of your microinertia. These bits of your microinertia just don't show up. You don't know anything about them so far. Okay, so fine. You go back to the equations. What does J satisfy in general? What it satisfies this equation. I mean, M is 0 when you haven't taken the derivatives, and then later when you put derivatives there, you'll have some stuff. So now the point is, you should think of this as essentially a transport operator. It's like an advection rotation operator. It's transporting things and then rotating them. And so you get good LP estimates, basically. Okay, so this is the, okay, this is not super important. The point is, with the time we have left, the point is from this is a hyperbolic part. So the problem is, all it tells you is that the HK norms of J, well, it's only hyperbolic, so you have this right-hand side that shows up from U and omega appearing here, right? So a priori, this could be growing in time. So the point is you have a problem from the hyperbolic part because this could be growing in time. Okay. And now comes the part where you suffer because now you have to make sure all of these things talk to each other in a good way. And this is going to be summarized in one slide, but so I have an energy estimate. I control this plus a dissipative term. And then I know from this was the explanation for why we get algebraic decay, not exponential decay, that if the energy, when I take a lot of derivatives, is bounded, then the energy at a low level decays. Okay, that's nice. So that tells me that at lower regularity, I expect U, omega, and A to decay, and at higher regularity, I expect them to be bounded. That's nice and good. And then from the transport estimates, well, I just get this. So at the high regularity, these things could grow. Yeah. Okay. So now the problem is this: you get interaction terms like this, and this is where things get just nasty because 20 of the interaction terms look fine, and then 21st looks bad, and go back to figuring things out. Interaction terms like this are particularly nasty. Why? Because what you're looking for, right? Your interaction terms manifest in this way. So you want to try and absorb them. You're doing stability. You're in a small, your energy is going to be small. So you want to absorb them in this way. Okay. But this is bad because you have A with a lot of derivatives on them. This is exactly the thing that we couldn't put in the dissipation. It's exactly why we had algebraic and non-exponential decay. So this is bad. So if you try to put this in dissipation, you're dead. There's no chance. So you integrate by parts and you get something like this. Now the problem is now you have this at a high level of regularity, which is only growing in time. So now you have to be very careful of making sure that when these things show up, they're next to something at a low level that decays, and that on balance, these things are under control. So sort of very schematically, those are the games you have to play to balance and make sure that the stuff that is potentially growing, I mean, the estimates don't tell you it's doing anything better than growing. Not really expecting that physically. You need to make sure that what's potentially growing from your hyperbolic part is under control from the. And then, okay, additional technicalities is that you don't get this pointwise, you get this intermediate time. So when you do all of this, if you're a pancake, so your single eigenvalue is larger than the repeated one, your equilibrium is still the same. But now the equilibrium is stable. So you have to be, taking out derivatives of the thing to get off the ground, but that's fine. You have a delta ball in HK, or if you start in that delta ball, you'll approach the equilibrium at this point. And once again, anisotropy is sort of the driver of the interesting things happening. There is hypocoercivity at the linear level, right? There's this thing that you don't have the dissipation controlling energy. You have these estimates involving advection rotation operators are there because this would be purely advection if you didn't have a precession. And you have these parabolic interactions at the nonlinear level that you have to be careful. So in conclusion, too fast. Where do micropolar fluids come from? They come from imposing a rigid microstructure or rotating microstructure in the context of continuum mechanics. And then subject to a uniform microtorque, you get two cases. If you're a rod, you're unstable. You don't know this, but you're expecting to topple over and rotate. Whereas if you're a pancake, you're just rotating. It's like a vinyl, like just rotating at a constant rate, and it stays there. And the anisotropy led to a bunch of difficulties in those places. In the unstable case, we had to get our hands dirty with some complex analysis to find the eigenvalues. In the unstable case, you had the lack of a spectral gap, which means you have to do nonlinear estimates in a particular way. In the stable case, at the linear level, you have this lack of coercivity, this controlled energy, you get a coarse decay rate than you would otherwise. And then at the nonlinear level, in the stable case, you have these interactions between parabolic and hyperbolic force. And I think that's it.
Questions?
So about the stable case, so you use this hypocoercivity, but I guess you should also have the spectrum analysis exactly as in the unstable case, and you computed the asymptotic form of the eigenvalues, and then you would get the same algebraic rate, no?
Yeah. I mean, in some sense, the algebraic rate is a manifestation of the eigenvalues now closing in an imaginary axis from the other side. Yeah.
But then I guess that actually in that case, you get exactly what you get an exact exponent for the algebraic rate. It's, maybe so it's telling you that actually this is the optimal.
Right. So yes. Okay. So the algebraic decay is not as one reviewer put it that we didn't try hard enough. Is that the linear thing tells you these things are getting close to the imaginary axis, so you're not expecting better than this. Yeah. And there's work like this on, but in the context of the viscous wave problem, where they're looking at the linearized thing, and they show that for the linear problem, it's exactly the decay rate you get is the one from this hypercoercivity. So it's a feature of the linear part of the problem. Yeah.
I have a very niche question. It's not mathematical at all. So, Waitrose used to do like take home rice in paper bags, like fill up paper bags, rice and carry them home. And you get home and you pour them out into another container. And as they're pouring, in the beginning they behave like a float, kind of pouring nicely. And at some point, they stop doing that and they just start like pinging around inside the paper bag, and it's pure chaos. Can this model that? Like, do you see what if not, what feature of this model would you need to add to see that transition from like fluid behavior, and there's a big bulk of them, they're all, I guess, suppressing each other, to non-fluid what feels like it feels like a gaseous material, or like a fluid. Maybe this is not related, but they're also like rocks.
So I guess one question is about what's going on here in terms of, I mean, if you have base where there's no rise constant amounts, there's some gaps in between. I mean, this is all based on sort of continuing formulation of these things.
Yeah, I guess
like
there's
vacuum type thing.
Yeah.
It's,
Okay.
at least the way I've motivated it. Then, so, but I'm not sure I was the right picture from description. This is also related to what you were talking about at the start in terms of rho and things like this. The description, the motivation of the system in this way makes sense in this way for incompressible things. For compressible, it's a bit messier because the mass is additive, you're fine, but moment of inertia, not so much. So things get more complicated. When you have just for the compressibility.
And what about suspensions? So if you imagine like rice in a big pan of water, like loads of rice and loads of water, so there's fluid in between the rice grains.
Also in the engineers, like Aaron posited all this, they claim that this works as long as you have like some sort of packing function, right? They don't need sort of two jam together or something like this. But if you have dilute suspensions, they say that this gives you, for example, in the case of the medium at the very beginning, the point is because of these additional viscosity terms you get, that lets you compute the effective viscosity better than if you didn't take into account the fact that there is stuff in the fluid, the synovial fluid medium. So in that sense, I mean, there it is exactly that. It is a suspension. And
Modeling
they
is
get
it's
the
not a
model
suspension.
Yeah, I mean, the way I presented it and sort of the formalism of the way you're deriving these things, yeah, you're not really assuming a mixture. But it turns out it works as long as it's sufficiently diluted. That's an interesting question of where that threshold could be.
Right.
This was working.
The initial presentation has zero total momentum.
Sorry.
The initial presentation has to be zero total momentum. Is that right? Integral of U. You need to apply for the rate.
Yes.
Yes.
Yeah, but you have that.
We do a similar feature for the angle.
No, because you have the full. I think it's probably okay. Maybe it's going to take long to find it, but you have the full. So because there's this coupling term between U and omega, with this curl of U minus omega term. And so you control that term in the dissipation. So then once you control the grain of U, you then also control that omega. So you control omega in the full H1 of dissipation.
So that is for omega.
It's the full H1 thing. Yeah.
Any other questions? All right, let's thank Antoine. And that concludes the James